All right, welcome back. We're going to continue our journey into Chapter 9, and we're going to talk about the central limit theorem for sample means. Okay, so we talked about central limit theorem for sample proportions, and now we'll change it up and talk about central limit theorem for sample means. So the sampling distribution of the sample mean is approximately normal so this notation here is saying it has a normal distribution. The first number that comes before the comma, that's the mean of the normal distribution, and the number that comes after the comma is the standard deviation of the normal distribution. So what we're saying is that the sample mean, we can approximate it using a normal distribution with the mean of the population and standard deviation of the population divided by the sample size here. But because this is remember, sampling distribution is just a probability distribution function, but it's special because we're using a statistic or an estimator here. So really the standard deviation, they call it standard error. Okay, standard error. And what it means, it's the standard error, it's pretty much what this is right here. It's the expected error between our estimator, x bar, and the true value mu, okay, the population mean. Okay, so this is true. This is all true as long as, so these conditions are pretty much the same as they were for sample proportion, but there's a slight difference in number 2 here. But number 1, you have to have a random sample and independence. So each observation is collected randomly from the population, and observations are independent from each other. The sample can be collected either with or without replacement, but typically it's without replacement. 2. So large sample, well, sort of. If the population distribution is normal, okay, the population, the individuals, if it's normal, then any sample size will work. Doesn't matter, okay. Or the sample size, or we don't know the distribution and the sample size is large. And large, we're saying here at least 25. Okay, so right away when we're doing sample proportion, we had to check 2 conditions, right? N times P at least 10, N times 1 minus P at least 10. Obviously they're different here and dealing with the sample mean. Okay, so and of course we need big population. Of course, if we're sampling without replacement, that's what simple random sample means here, then the population must be at least 10 times larger than the sample size. So 1 and 3 are identical to what we saw for sample proportion, but in terms of large sample, well, we're saying here, well, it depends. It depends. So let's see an example here. So we're just saying, why is a sample mean of several runners a better estimator of the typical race time than a single observation, right? So we're just saying that the collection of individuals' input, the average of it is going to be better than a single observation, right? Even no matter where this single observation is coming from. Okay, if it's coming from some expert, we're saying the average of just randomly selected individuals is better and more precise than a single observation. So here we say the population distribution of finishing times for these runners is close to normal, with population mean 91 minutes and population standard deviation 16 minutes. So this assumption that's given here is very important. Okay, it's very important. Okay, so what it's saying in terms of number 2 condition that we had prior is that what we're about to do will work for any sample size. Okay, so what they're saying here is that the distribution of run times of individual runners, okay, single runners, their mean finishing time is 91 minutes with standard deviation 16. Okay. So now we ask, what is the probability that the finishing time of a single randomly selected runner is within 10 minutes of the population mean? Okay, so within 10 minutes, it means within 10 minutes of 91. So it could be 10 or less. It could be between 101 and 81 minutes. Okay. So if I go in here into StatCrunch, okay, well, if we're looking at individual times, okay, my mean is 91, my standard deviation is 16 minutes, and I want to find the probability that it's within 10 of 91, so that's really just from 81 to 101. That's within 10 minutes. No matter which time you pick here in this interval, the absolute distance will not be greater than 10 minutes. Okay, so you find this probability, you roughly get a 46.8% chance. All right, so if you're, so kind of what it's saying, if you're just using one person's time to estimate the average, right? It's saying, well, that one person, the chances that their time is even within 10 minutes of the population mean is roughly 46.8%. Right, 46.8%. Right. So what we're going to do here now is, well, what if we looked at the average? Okay, what if we just looked at the average wait time here? Okay, what can we say about that? So in the next step, what we're going to do is we're going to say, what is the probability that the finishing time of a sample mean of 9 randomly selected runners is within 10 minutes of the population mean? So that's the real big change between with the central limit theorem. If it's a probability involving the mean or the average, that's screaming at you that we're using the central limit theorem here. Okay, that we're going to do normal with some standard error that's divided by the sample size. Okay, so here, I mean, our sample size is 9. Obviously, it's not larger than 25, but remember, this comes from a normal distribution, so it'll work for any sample size. And in actuality, it's not even central limit theorem. Okay, this is the exact distribution of the sample mean. Okay, but you know, they keep it simple and just throw it in the central limit theorem conditions, but this is exact. Okay, so here, so what happens is the distribution of the sample mean, well, it has the same mean, but its standard deviation, or now this is called the standard error, is smaller, right? Because we're doing 16 divided by 3, right? So when I plug this in here, I have my mean of 91, and my standard deviation is 16 divided by 3, and I get 5.33. So that's my new standard deviation. And I find the same probability, and look what I get, 93.9%. So this probability practically doubled when we're looking at the sample mean. So what it's telling us is that if you're using a sample mean of just 9 to estimate the true mean, right, it's much more likely that the sample mean is going to be closer to the true mean. Okay, because you're using just one runner, it's like 40% chance that it'll be within 10, right? But if you're using the average of 9, look at that, you're at about 94% chance of being within 10 of the mean, right? So what central limit theorem is saying also is that together, all our information put together is very powerful, okay, in estimating, right, versus a single observation. So just as a reminder, so I mean, as far as so we used a result there about the average, and of course we have to justify it. So here we're saying the sampling distribution of X bar, actually it's exactly, okay, not approximate, normal with this mean and this standard error. Okay, population mean was 91, and population standard deviation was 16, and 9 was our sample size. So here we're saying each runner is collected randomly from the population. The runners' finishing times are independent from each other, and of course, I'm sure this is sampled without replacement. Okay, but you know, we just didn't pick like the first the runners who placed in the first first place to 9th place, right? We randomly selected them. Okay, and as far as large sample, well, not really. We don't really need a large sample because we know the distribution of times is normal. Then any sample size will work. Okay, and the last is big population. So if the sample of 9 runners was collected without replacement, which it was, then the population of all runners must be larger than 90, right? So that's 9 times 10, right? At least 10 times larger than your sample size. I think it's safe to assume that for this data here. Okay. So in this next example, what we're going to do is you're not going to know the distribution of the population. Okay, so it's not going to be normal. So in this case, we definitely need a large sample size. Okay, to estimate probabilities involving the sample mean. So in this example, we're saying according to one very large study done in the US, the mean pulse rate of adult women is about 74 beats per minute, okay, BPM, and the standard deviation is 13 beats per minute. And what it's saying is that, well, as far as the distribution for individual BPMs, it's just saying, well, we don't know it, but we know it's skewed to the right. Okay, so what's telling you is that, you know, there's quite a bit of BPMs out there that run pretty high. Okay, pretty high, and they're kind of skewed out to the right. Okay, so so in this example, suppose we take a random sample of 36 women from this population. What is the approximate probability that the average pulse rate for this sample will be below 71 or above 77? Right, so in this case, we're not given that the distribution is normal. Actually, they don't even know the distribution. They just say it's skewed right. But central limit theorem doesn't care, okay? Because central limit theorem says, hey, just give me the mean, give me standard deviation, give me at least 25 sample size, and I will make it normal, okay? Okay, so let's look at this example here, okay? So before we go on to find this probability, let's just verify our assumptions here. Okay, so here I'm saying sample distribution of X bar is approximately normal. Okay, so this is just an approximation. Okay, so our probabilities could have a slight error in it. Okay, larger sample size, the better the approximation is. Okay, so here we're saying 74 beats per minute is the population mean, 13 beats per minute is the population standard deviation, and our sample size is 36. Okay. So this is true as long as we have a random sample and independent. So we're saying each woman is collected randomly from the population, and the woman's BPM are independent from each other. And as far as large sample goes, well, in this case we do need a large sample because the population distribution is not normal and is skewed to the right. But we have a large sample of 36, so which is greater than 25, so that will work. And of course here, you know, the sample of 36 women was collected without replacement. So then the population of all women from the U.S. must be larger than 360, or at least 360. Okay, so all I did was, you know, 10 times the sample size. So I just do 36 times 10. All right, so it has to be larger than that. So all this checks out, so we can move forward. So now I just go into StatCrunch here, okay, and calculate the probability. But I have to do a little extra work because really we want 71 or below or above 77. So StatCrunch won't give me that. So what I need is the area in the tails here. I need this. This is 71 or below, and this is 71 or greater. That's really the area that I need. But StatCrunch won't give those to me directly all in one shot. So what I did here is I plugged in a mean of 74 and I put in the standard error. Okay, so remember the standard error here is 13 divided by the square root of 36. So 13 divided by 6 will give me the standard error for the sample mean, which is the standard deviation. So here I plug in, I find the sample mean between 71 and 77, and I get 0.833. Right, so it gives me this red shaded region. Right, so if I were to add this area, plus this area, plus this area, it would equal to 1. So if I did 1 minus this red shaded region here, I will get the probability that's in these tails here. Okay, so that's what I did here. I just did 1 minus the area being in between, which is equal to 16.62% chance. Okay, so what this is saying is that if the average BPM of 36 women, there's approximately 16.62% chance of observing a sample mean of 36 women being less than 71 or greater than 77. Okay. So now we ask, just like how we did before with the runners, we did single and then the average. So now we ask you, can you find the probability that a single adult woman will have a resting pulse rate more than 3 BPM beats per minute away from the mean value of 74. And so the thing is here is that if we look at what we're given here, it says, okay, we have the mean of 74, and we have standard deviation of 13, and then the distribution is, it just says skewed to the right. So actually we don't know the distribution. Okay, we don't know. I need a probability distribution function in order to find a probability, and right now I don't have it. Okay, so right now we just say nope, we can't. Okay, we don't have enough information. Okay, but what was really neat though is that, well, if we're talking about averages, we can approximate the probability. So that's the power behind the central limit theorem. It takes, no matter the distribution of your population, if you're just taking averages, right, these things magically become a normal distribution. If you're looking at average behavior versus individual behavior, average behavior tends to follow a normal distribution. Okay, and what the central limit theorem is saying here is that, look, we don't even need to know the distribution. Okay, we don't even need to know it. I could put right whatever I want here, as long as I don't know the mean, as long as I know standard deviation, I can find the approximate distribution. Okay. So one thing to know here is, in looking at these graphs, okay, so here, as far as the population goes, right, I can pick, with StatCrunch, I can pick whatever population that I want here. Okay, I can really mess up the population. Okay, so for example, let me just show you real quickly how we do that. I'll go here, let me go to applet, and let me go to sampling distribution. Okay, so I can give it, I could do uniform, I guess, and then I can do compute. Okay, I could do uniform, I could change it up, I could do, maybe 100, or I could put -25 to 100, it doesn't matter. Okay, compute it there. So you see when you put your mouse over here, it turns into a little plus sign. Well, look, I could do this. Making my own custom distribution function that's multimodal and just out of whack here, okay? So this is just some distribution. I'm just making one up. It's just a crazy distribution. It's multimodal, but this is the distribution of the population, okay? And so one thing you should be able to tell is, first of all, this is distribution of the population, okay? Now let me take a sample of, say, 25. Okay, and so let me take a sample of 25. So let's see what it looks like one time. Okay, so these are 25. This is my random sample of 25 that I collected from this population. And then I took the average. Okay, so let me do this about 1,000 times to get the sampling distribution of the sample mean. Oh, look it, normal again. Okay, so from here, right, this is distribution of the population. This is my observed random sample. And this is my sampling distribution for the sample mean. Now, I'm going to replace 25 with 250. Okay, so my sample size is going to be 250. What do you think my normal distribution, my histogram is going to look like down here? Do you think it's going to look the same? Do you think it's going to look wider or a little bit narrower? What do you think is going to happen? And so these are things you need to be able to visualize here, but what I'll do here is I'll just run it. Okay. So here I'm observing 250. I have a random sample of 250 from this population, right? And if you look at this, it's still kind of unimodal symmetric, still has the same mean, but one thing that you notice that it became a narrower. Okay, the standard deviation decreased. Right. So just by looking at these pictures of these distributions, right, we could tell when the sample size increased or decreased. So definitely, in looking at this, we could tell the sample size increased because the standard error became a lot smaller. Okay, so that's what this is doing here. Okay, so in here I have a sample size of 100, and over here I have a smaller sample size of 25. So I mean, without even showing you the sample sizes, you see this sampling distribution of the mean, this sampling distribution of the mean. It should be obvious that this here had a much smaller sample size than this here. So when we're talking about the average or reporting probabilities here concerning the average, you always have to state, well, this is probably the average of 36 or 25. You always have to state how many outcomes are in your average, because for different sample sizes you get slightly different distributions. Okay, so when we're talking about the average, make sure you state the sample size that was used for that average. Okay, now the last thing that we'll touch on really quickly is the t-distribution. So when we do hypothesis testing and confidence intervals, a lot of times in practice, we don't know sigma. Okay, we don't know sigma, so which is the population standard deviation. So we have to replace sigma with S, which is the sample standard deviation. So, and that's the sample standard deviation from the earlier chapters from week 1, right? So when we're working on testing, calculating hypothesis tests or confidence intervals, or we have to introduce what we call the t-test statistic, right? So what we're going to do is we're going to compare the sample mean to a null hypothesis mean, and we want to know whether this difference is significant or not. Well, what we want to do is compare it to the standard difference, right? The standard error. And remember, what this represents is the typical distance that we should see between the sample mean and the null hypothesis mean. Okay, but in this case, we don't know sigma, so we have to estimate it with sample standard deviation. Okay. So what happens with the t-distribution, so in dealing with confidence intervals, we had like z star, right? We had to find out what z star is. So now we're going to have to deal with something called t star. But one thing to note is that this t is telling us that we're using not a standard normal distribution anymore, but a student's t distribution. So the distribution is unimodal and symmetric, but its final shape is determined by its degrees of freedom. So degrees of freedom, they're equal to your sample size minus 1. So here I had a sample size of 6, here I had a sample size of 14. So sample size of 6 minus 1 is 5 degrees of freedom. So if you look at this distribution, right, so this curve here, that's like the standard normal. So you compare this distribution to the normal. I mean, it's symmetric about 0, it's unimodal, but it's flat. See, it's kind of pushed down, the top is pushed down. So there's a lot more variation around 0, a lot more variation around the mean. And that should kind of make sense, because in this statistic here, we're really trying to estimate the mean, right, with the sample mean, right? And we want to know whether this difference is significant, right? But here, we don't know, we don't have sigma, so therefore we don't know what the true standard error is. So we're estimating it here. Right, so we have to back up a little bit, and we can't be as precise as we want to be, and that's what this t-distribution is reflecting, because there's a lot more variation, right? But when you increase your sample size from 6 to 14, right, because that's 14 minus 1, you see this this peak gets pulled up a little bit, right? Meaning that there's a little less variation around the center, right? Still a little more than the standard normal, but considerably less. So kind of what that's saying is that, well, as your sample size increases, we can trust this estimate more and more, right? And as sample size becomes larger and larger and larger, right, this value here is pretty much the same as sigma over root n, population standard deviation over root n. And so that's what happens. These degrees, so this is the same degrees of freedom with infinity, but really, like, once your degrees of freedom hit about 30, the t-distribution curve, because it's gonna, as sample size increases, this peak just getting pulled up, and then it doesn't go past this point. So as degrees of freedom increase, it's going to get closer and closer to a standard normal distribution. And what that's saying is, well, you have more data, so therefore you can trust your estimates a little more. But if you don't have a lot of data, well, you can't trust them that much. You can't trust them that much. Okay. But we're going to see more of this when we derive confidence intervals in the next section.